Hi everybody, welcome to another video in Pre-Calculus, section 3.5, the graph of rational function. These are a few steps that we can do for a rational function. So first, we'll state the domain of the function. The domain, as stated before, is where the denominator not equal to 0. So if x squared minus 9 not equal to 0, meaning x squared not equal to 9, taking the square root on both sides, x not equal to plus or minus 3. Yeah. So the domain we just said, we can say just the set of all the x such that x is not equal to 3 and x not equal to negative 3. So that set builder notation, or we can say we can write everywhere except negative 3 and 3. So negative infinity to negative 3, negative 3 to 3, and 3 to infinity. It's not including 3 or negative 3. So any of this is fine. Right, so that is where we have the domain is where the denominator not equal to 0. The x-intercept, we have to intercept the x-intercept and the y-intercept. X-intercept is where we let y equal to 0. So we will let this equal to 0. Right. So this is 0 equal to 0 when the top is equal to 0. So if x equal to 1. So the x-intercept is we let y equal to 0 and we solve for x. So we have x equal to 1, y equal to 0. Right, so that is the x-intercept. Let x equal to 0. For the y-intercept, we'll let x equal to 0. And we solve for y. X equal to 0. Negative 1 over negative 9, that is 1 over 9. So the point is we have x equal to 0, in that case y equal to 1 over 9. So that is the point, y-intercept. The asymptotes, we have vertical asymptote, horizontal asymptote, and the slant asymptote. So vertical asymptote is where we let the bottom equal to 0. And then the top is not. Right. So bottom equal to 0, we have x squared minus 9 equal to 0. Solving for x. So x equal to, if we take the square root on both sides, don't forget there's a plus or minus. So we have plus or minus 3. Now at x equal to 3, I will put 3 on the top. And that is not equal to 0, so which is good. So that means x equal to 3 is a vertical asymptote. And then we check at x equal to negative 3, top equal to negative 3 minus 1, and that is negative 4. And that also not equal to 0, which is good. So the top is 0, the bottom is not. So that's why we have the vertical asymptote. Now, remember we have vertical asymptote, horizontal asymptote, and slant asymptote. If we define a rational function being the ratio of two polynomials, in that case we either have the slant asymptote or the horizontal asymptote. We cannot have both. Once again, either the slant asymptote or the horizontal asymptote. We cannot have both. But for that, we will find the degrees. Degree on the top. Degree on top is 1. Degree at the bottom 2. So what we have is degree on top is less than the bottom. So if degree at the bottom is bigger, y equal to 0, is the horizontal asymptote. If we have the horizontal asymptote, we do not have the slant asymptote. This is only when we have the ratio of two polynomials. If it is between two different functions, that might be different, but ratio of two rational function. Of course, if we define, remember this is way back in trigonometry, tangent is sine over cosine. Of course, the tangent we have there will be a bunch of different horizontal asymptote and for tangent. And of course, the tangent inverse, there are two different horizontal asymptote. But like I said, in this section we only worry about, in this chapter we only worry about the ratio of two functions, the ratio of two polynomial functions. So we have the horizontal asymptote, which means there's no oblique asymptote or no slant asymptote. Either horizontal asymptote or slant asymptote, cannot be both. Right. Check to see if the graph intersect the horizontal asymptote. So we will let this equal to the horizontal asymptote of y equal to 0. So we have y equal to x minus 1 over x squared minus 9. And we'll make that equal to 0. And the reason we use 0 because the horizontal asymptote is y equal to 0. Put 0 in that and make the y equal to the asymptote, the horizontal asymptote. So of course, once again, we multiply x squared minus 9 on both sides, or just if a ratio, if it is in reduced form, then it is equal to 0 when the top equal to 0. So we have x equal to 1. So the answer is yes. The graph will cut the horizontal asymptote at x equal to 1. Alright, keep that in mind. Now, check a few more points. We know that -3 and 3, it is undefined. So let's, and then we have, so what point do we have at this point? Let's just list all the points we have. So x-intercept, uh, 1 and 0, y-intercept, 0 and 1 over 9. And then we can choose a few points. We can choose like 2. We're not going to choose -3 and 3, right? So we say undefined. It's x equal to 3 and x equal to -3. So we could test like at x equal to 2. So put 2 in this. So if we just do this, put in the function x minus 1 divided by x squared minus 9. We'll go to the table and then we have quite a few values. When x equal to 2, y equal to -0.2, which is -1/5. And when we have -1, we have 1/4. Yeah, and so on. said, just a few points. Right. It's easy. Put x values into the function, find y values. Right. Next, we will do this design chart to get better idea of what the graph of the function will look like. So what we have is, it is undefined at 3 and -3, right? So we have -3 where the function is undefined, and 3 where the function is undefined. When x equal to 1, the function equal to 0. So we'll divide this like a table, right? So we divide where the function x, where x, that makes the function equal to 0 or undefined. Because if we have a number, if there's potentially a number, therefore possibility equal to 0 does not exist, and greater than or less than 0. So it is 0, does not exist, greater than or less than. So we know that it is equal to 0 when x equal to 1. It is undefined when x equal to -3 and 3. Now we just need to know what happened if it is not those numbers. So that's why we have the sign chart. Of course, if it is not 0, if it is not undefined, it can only be positive or negative. So we do the test point, pick a number between those intervals. So I choose -4, 0, 2, and 4. Put in the function. If I put -4, I have a negative number. If I put 0 in, I have a positive number. Put negative, I put 2 in, it's negative. And put 4 in, it's going to be positive. So that's what we have. Right. Now, the graph. Put all the features that we have. First, we have two vertical asymptotes. So that we put that in first. So the asymptote is not part of the graph, so that's why we're gonna do that in the dash line. Horizontal asymptote is y equal to 0, so that's here. So there's a vertical asymptote here, vertical asymptote, and horizontal asymptote. Right, next. That's why we test some points. We have 0 and 1 over 9. That is the y-intercept, x-intercept. If we put 2 in, we have -1/5. So we have those 3 points. And then notice that between -3 and 1, between -3 and 1, the function is positive. It can only be positive. And it has the vertical asymptote here. So therefore, from -3 to 1, it's going to be positive. And from 1 to 3, it is negative, and it approaching to the vertical asymptote. And finally, if we have the point here, and from 3 to infinity is positive, so it has to be that. Yeah. So we have, of course, it's going to be that. So we have the vertical asymptote and horizontal asymptote first, and then we choose the point in between. We know the graph we approach to the asymptotes. So that's what we have. Right. So to summarize what we have, the domain is where the bottom equal to 0, not equal to 0, right? Because we cannot divide by 0. So denominator not equal to 0. X-intercept, let y equal to 0. Y-intercept, let x equal to 0. Vertical asymptote is where the bottom is 0 and the top is not. Notice that the vertical asymptote is where the function is undefined. So kind of opposite to this. opposite to the domain. Horizontal asymptote, we use the degrees, so degree of top and degree at the bottom. And the slant asymptote is where degree is on the top is 1 more than the bottom, quotient not equal to 0, then just keep saying that, sorry, let me just write down. Where degree on top is 1 more than the bottom, and the remainder not equal to 0. Because the slant asymptote or oblique asymptote, and when that happened, then we have y equal to the quotient. Quotient is the slant asymptote. Right. Determine if the graph crosses the horizontal or oblique asymptote. So that we just do that, and then we solve for the top equal to 0 and bottom equal to 0, so we can have the sign chart. The top equal to 0. If it is reduced, give us y equal to 0, and the bottom equal to 0 is undefined. Of course, you said, what happened if both of them equal to 0? Well, if both of them equal to 0, that should cancel out the common factor, and we should have a hole in the graph, then the sign chart, and then graph. So let's look at 2 more examples. Right, let's analyze and graph this function. Right, so first, the domain, once again, is where the bottom or the denominator not equal to 0. So just x not equal to 0. Right, so everything but 0. Intercept, there will be x-intercept and y-intercept. X-intercept, let x equal to 0. I'm sorry, let y equal to 0 and solve for x. And then solve for x. So y equal to x squared minus 4 over x equal to 0. If it is equal to 0, the ratio, then the top is equal to 0. Of course, that is reduced. So x squared minus 4 equal to 0. So x squared is 4. So x equal to plus or minus 2. Yeah. So we have the x-intercept. Up 2. Y equal to 0. X equal to negative 2. Y equal to 0. Y-intercept is where we let x equal to 0. Now if we let x equal to 0, the bottom is equal to 0, the function is undefined, so there's no y-intercept because the function is undefined when x equal to 0. Right, asymptotes, there will be 2 kinds, vertical asymptote or horizontal and slant asymptote, either one of them. Right, so vertical asymptote. Bottom equal to 0 and top is not. Bottom equal to 0, we have x equal to 0, and at x equal to 0, top equal to 0, square minus 4, which is not equal to 0, which is good. So we don't want the top equal to 0 And that's exactly what we want. Bottom is 0, the top is not, which is exactly what we have. Right, now we either have the slant asymptote or the horizontal asymptote. That depends on the degree. So what we have degree here, degree on top is 2, degree bottom is 1, so the top is bigger than the bottom. So this we have no horizontal asymptote. And then is there a slant asymptote? Right. So remember, we do two things. First is degree on top, 1 more than the bottom. Degree on top is 2, degree bottom is 1, 2 equal 1 plus 1, so yes. And then we divide. Well, divide is relatively easy, but it's the remainder. Not equal to 0. Well, let's just divide. Sorry. Just try to divide here. Right. So we take x, we go into x squared minus 4. X go into x squared, x times, multiply back, x squared, subtract, we have 0x minus 4. So yes, this is the remainder that is not equal to 0, which is good, and the quotient is x, so the slant asymptote is y equal to x. Yeah, so quotient, y equal to the quotient if the remainder is not equal to 0, and if the degree on top is 1 more than the bottom. Next, determine if the graph crosses the asymptotes. So we will just let the function equal to the asymptote, which is x. Yeah. So substitute this, substitute the x. Yeah. And then we cross multiply over 1, and the cross multiply, we have x squared minus 4 equal to x squared. Well, subtract x squared on both sides, we have negative 4 equal to 0. That's not possible, so there will be no solution. Or just say no, the graph will not cross the asymptotes. Yeah, it can only cross the slant asymptote or the horizontal asymptote. It cannot cross the vertical asymptote. So it's no solution here, so it does not cross the slant asymptote. Now next, we just need to solve for the top equal to 0, the bottom equal to 0, so we can put on the sign chart. That's pretty much. Top equal to 0 is where the function equal to 0, bottom equal to 0, so y is undefined. So at the top equal to 0. Yeah, a lot of these are redundant. X squared equal to 4, so x equal to plus or minus 2. Yeah, plus or minus square root 4, which is plus or minus 2. And the bottom equal to 0, x equal to 0. Right, so the sign chart, we have the values of 2, negative 2, and 0. This is raw chart. So here, first we have x values on the number line. The special values. The special values here we have 2 and negative 2. And then we have have 0 for the function x squared minus 4 over x. Now, when x equal to negative 2 or 2, y equal to 0. So we have 0 here for y. And when x equal to 0, the function is undefined. So we have negative 2, 0, and 2 divide the number line like that. Then we choose a number in between the interval, be negative 3, negative 1, 1, and 3. Choose a number between the interval and test them. We have x squared minus 4 divided by x. Let's go to table. When x equal to negative 1, it is 3. Yeah. It's 3. X equal to 1, it is negative 3, but it's negative. When x equal to 3 is 1.667, that's like 5/3. Yeah, we can just do this variable, y variable function, y1, evaluate at 3, and convert to fraction. Yeah, that would do. And then negative 3. It's negative 5/3. Why? They put the wrong place. Yep, I did. Yeah. Right, so that's what we have. Yep. Those are the points and those are the sides. Yeah, it's good to have the values too because we're going to plot the points anyway. So if we have the points, you just use those. Alright, so first we graph any asymptote. We have 2 vertical asymptotes. Sorry, 1 vertical asymptote. X equal to 0. So we have the vertical asymptote x equal to 0, which is the y-axis, right? So this is the vertical asymptote. Right, try to put all the points we have. The x-intercepts 2 and 0, negative 2 and 0. Y-intercept there will be none because that is where the vertical asymptote at. We have the point when x equal to negative 1, it is 3. And when x equal to 1, it is negative 3. X equal to 3 is 5/3. 5/3 like 1.67. And then when x equal to negative 3 is negative 5/3. So we have those points. Right. In this case, we do have the slant asymptote of y equal to x, which is the diagonal line here. And since we have those 3 points and we know the function approaching to the asymptotes and it will not cross the slant asymptote, so we have to be like this. Right. Of course, that's what we have. If we draw the slant asymptote into the function, let's draw that as a dotted line. That should be dotted, but anyway, yeah, so that asymptotes. Right, simple enough. Try another example. Right, the domain. Domain is, of course, denominator not equal to 0. So x squared plus x minus 6 not equal to 0. So let's factor it. X plus 3 and x minus 2 not equal to 0. So we have x not equal to negative 3 and x not equal to 2. Right, it's good enough. Of course, all the different notation. Yeah, but just give x not equal to negative 3, x not equal to 2. Good enough. Right, we know where the function is undefined. Now for x-intercept, let y equal to 0. Right. So y equal to 0 meaning that the top equal to 0. Of course, we can factor out the 2x. So if x equal to 0, x equal to 1, so there will be 2 x-intercept. When x equal to 0, y equal to 0, and when x equal to 1, y is equal to 0. So 2 x-intercepts. So 2 x-intercepts. Now for y-intercept is where we let x equal to 0. Well, x equal to 0, then y equal to 0. Well, that is obvious. So that is, of course, 0 over negative 6, which is 0. So once again, the y-intercept is also the x-intercept in this case, 0 and 0. Right. Notice that the only thing we need to check for is the x-intercept. The x-intercept, this values is going to be different than this, right? Yeah, because potentially we might have the case where both top and bottom equal to 0. It's not this case. So whenever we find for the x-intercept, make sure that the it is different than the domain. It is in the domain. That's what I mean. So 0 and 1, of course, different than those points. Yeah, just make sure that. Right. Vertical asymptotes. Bottom equal to 0. And the top is not. So bottom equal to 0. I said a lot of this are redundant, and we did solve for this. We did factor as is x plus 3, x minus 2. So we have negative 3 or 2. So x equal to negative 3. Of course, when we solve for the domain, is x not equal to something, and then the vertical asymptote, we can just let x equal to those numbers. So domain and the asymptotes, those values complement each other. X equal to negative 3, the top. Negative 3 squared is 9 times 2, 18 minus 6 is 12. It is not equal to 0. So yes, we have one vertical asymptote there. Now, when x equal to 2, we put 2 in for x. 2 squared is 4 times 2 is 8 minus 4 is 4. And once again, that is not equal to 0. So yes, so those values make the bottom equal to 0 and the top is not. Right. As far as degree goes, degree on the top is 2, degree at the bottom is 2. So if degree on top equal to degree at the bottom, we have y equal to the ratio of leading coefficient. Y equal to, we take the, pretty much divide those highest terms. If the degrees are equal to x squared cancel out, we have 2. So y equal to 2 is the horizontal asymptote. If there is the horizontal asymptote, there will be no slant asymptote. Next, determine if the graph crosses the asymptotes. So make that equal to, and see if there is 2x squared minus 2x over x squared plus x minus 6 and equal to 2. Yeah, just make it the quotient 2 over 1, so we can cross multiply. So 2x squared minus 2x equal to 2x squared plus 2x minus 12. 2x squared cancel out. We have minus 2x equal to 2x minus 12. Move the 12x over negative 4x equal to negative 12. So x equal to 3. So it will cross the horizontal asymptote when x equal to 3. Next, we solve for the top equal to 0, the bottom equal to 0 to get the sign chart. Right. Top equal to 0, when y equal to 0, bottom equal to 0, the function is undefined. By the way, if we have the rational function, if we can reduce the function first before we do this. So y is undefined. Because if both of the top and bottom equal to 0, at some point, those will give us a hole in the graph. So top equal to 0, 2x squared minus 2x is 0. I'll factor out 2x. So if x equal to 0, x equal to 1. And the bottom equal to 0, we already did. That is the in the domain. X plus 3, x minus 2. So if x equal to negative 3, x equal to 2. Right, the sign chart. X, there should be a lot of values here. 0, 1, negative 3, and 2. Right, negative 3, 0, 1, and 2. So negative infinity, infinity. Right. So it's negative 3 and 2. Those where we have the vertical yes, those are the vertical asymptotes where the function is undefined. when x equal to 0, x equal to 1, the function equal to 0. And we have the function 2x squared minus 2x over x squared plus x minus 6. Right. Now let's find the values. Choose a number in between the interval. So I choose a number first. How about -4, -1, 0.5, 1.5, and 3. Right, so we have 2x squared minus 2x divided by x squared plus x minus 6. Right. Of course, if we hit the table, there might be some numbers that's not integers, so we have to hit second. No, second, calculate, get the values. Of course, they give us the graph too, but yeah, we're going to use the graph, of course, but put the values. -4, it is -667, so that's like -2/3. Right. Wait, what did I put? -4. 667, so that's more like it just put 667. -1 is -2/3. -2/3. 0.5, it is positive, it's close to 0. 1.5 is -2/3, and then 3 is 2, right? It's positive. Right, so put everything we have here. The horizontal asymptote is 2. The vertical asymptote at -3 and 2. Right. And then a few points. When x equal to -4, -4 is -667, so about here. So wait, -4. So it's positive. Right, way up here. -1 is -2/3. 0.5 is very close to 0, and then 1.5. I mean 0 and 1, so we do have 0, 0 here. Those are the intercept at 0 and 1, and that point 1.5 is here. So, and since the graph approaching the asymptotes, it will be negative between 0 and -3 and 0, so it will be like this. And from 0 to 1 is also negative. I'm sorry, 0 to 1 is positive, but from 1 to 2 is negative. we have that point, and the function is positive. And then here is also positive. But it does cross when x equal to 3, y equal to 2, so it will cross that. However, it only crosses at one time, right? And it cannot be negative, so we will not go down. But because the horizontal asymptote, it have to go back and approach into it, so it have to be like this. We know for sure that even though we have the horizontal asymptote, it will not go like this, because we actually solve for it. The graph only cut the intercept, the graph only cut the horizontal asymptote exactly at one point. So that's why we do this, to see if potentially we have more intersection. It turned out to be no, there's only one of them. And we know they have to approach to the horizontal asymptote, so the graph will dip just a little and then have to approach into the horizontal asymptote. Even we have the graph on the calculator, on the calculator it won't even tell us that, but we know the graph will hit that point, but eventually have to go up and approach into the horizontal asymptote. It approach into, it will not cut the horizontal asymptote at any other point. So we have two vertical asymptote and horizontal asymptote. So that's what we have for the graph. Right. Yeah. Let's look at the whole problem then. Yeah. So like I said, some of this might be redundant, like the denominator at bottom not equal to 0, the vertical asymptote, the bottom equal to 0, and then so top equal to 0 or top not equal to 0. Of course we do a lot of those, but that's for different things. But put all of them together, the most important here we focus is the asymptotes. So we have the graph approaching to those asymptotes, and we have those points. So the graph approaching to the asymptotes, you can put an arrow saying if we want to. Yeah. We know that this will not cut the horizontal asymptote, it only cuts here, so they have to approach into the horizontal asymptote like that. Right. Now let's look at the application problem. Suppose a company that have aluminum cans cylinder with the capacity of 650 cubic centimeter, so the volume is that much. Centimeter cube. The top and bottom can are made of special aluminum alloy that cost 6 cents. 0.6 cent per square centimeters square. The side of the can made of a cheaper material of 0.03 per square centimeter. Express the cost as material of a can as a function of R, the radius of a can. So the volume of the can is this. Right? So first we will start with the volume is equal to 650, the base area. This is the base area, b pi r square. Base area times the height, we don't know, but that equal to 650. That's what we have for the volume. So here we can solve for h. Divide by pi r square. That gives us the height as the function of the radius. Next, to construct the can. To construct the can, we have to have two discs, one for top, one at the bottom. So the surface area, total surface area, we have top and bottom and the lateral surface. It is easy. Top is pi r square, bottom also pi r square, but the laterals, think about this, we have a piece of rectangular aluminum, for example. We're going to roll that to make a can. So in that case, the length of the rectangle is the same as the circumference of the circle, right? So that's why we have this rectangle is length times width. The length is the circumference of the circle, so we draw on the end and make a circle, and then the height is the width. So in that case we have 2 pi r h. That is the total area, right? But the cost is different than that because we focus on the cost function, right? The cost function says the top using 0.06, this is those price, and the bottom also use the same material. So we take the surface area, we multiply by the cost for 1 centimeter square, and then the lateral we use the cheaper material, 0.03. So combine this together, combine like terms, 0.06 plus 0.06, 0.12 pi r square plus 0.06 pi r h. Right. And then we will substitute that into h. So the cost function 0.12 pi r square plus 0.06 pi r h is 650 divided by pi r square. Cancel out a pi, cancel out one of the r. So we end up with the cost function 0.12 pi r square plus 0.06 times 650 that will be 39 divided by pi, divided by r. Pi cancel out, 1 r cancel out. So yeah, this is the function of the cost. Let's just graph the function. Let's see what happened. 0.12 pi, as it was x for r, plus 39 over r x. Look at the graph. Of course, this only works if r is positive, so the domain is right. Let's zoom out and see what happened. Right, so we have this. So it only works for r is positive, and of course, look like there's the minimum here. So we're trying to zoom this part. So it's zoom number 1. So I'm trying to zoom this part to find the maximum, I mean in this case the minimum cost. So let's zoom this window. Alright, that will be good. Right. So the function is like that. So there will be a minimum here. Right, so to determine the minimum, it's second trace, of course, the minimum number 3. So we look for the minimum. We'll go from the left, and then we'll go to the right. And when we hit enter, we will have the minimum when x equal to 3. So the r equal to 3.72, 7.26, and the unit should be centimeter. Of course, we can find the height after that. And what is the list cost? Well, it's 15.7. And the unit should be cents. Right. Yeah, this application problem, I just want to bring it up here so we, of course, derive that. The formula is nice and all, but just want to get let you use the calculator so we can graph the function. Originally, it is in this window, we don't see it. So in that case, we have to zoom out. So we see where the function at. Zoom out, and then we see the function at. And then we can zoom that particular window to find the maximum or minimum. So zoom number 1. Just like when we use the mouse, computer mouse, just select upper left and then lower right, hit enter, and we have the function. When we try to find the minimum or maximum, second calculate, go for the minimum. We have to give the left bound and the right bound, so the function will know on what interval it will search for. So it will search for the interval between those two, and first it will guess, and we hit enter, it will go straight to the minimum. And that's what we have. Right. And that's where I stop the video for this section. As always, thank you for watching, and see you in another video in calculus.